Hello students, in today's video we will be discussing about the combinational logic. So the basic thing is like, what is a combinational logic? You see, in digital systems we may have the logic circuit as combinational, or it can be a sequential one. A combinational logic circuit consists of logic gates whose output are determined directly from the present input without regard to previous output. And a sequential circuits are those which possess memory. That means they are basically the combinational circuits with memory. But in combinational, we don't have the memory in it. So in today's video, we will be focusing on the combinational logic circuit, and we will just see what are the procedures to implement the combinational logic circuit. So the first thing we will discuss about the combinational circuit is what it is. It is the combination of various kind of logic gates, and at any instance of time the output is based only on the level of current input terminals and not on the past state inputs. Uh, these circuits do not need any kind of memory, states, or clock, and a combinational circuit consists of input variables, logic gates, and output variables. So here we are having the basic, block diagram of the combinational logic circuit, in which you can clearly see that we can have the number of inputs and then the number of outputs, and then we can have in between the combinational circuit, which consists of the different types of the gates. And as I told you that it does not processes the memory, it depends upon the present input, and it has nothing to do with the previous inputs and all that. The concept of keeping the previous inputs and working with them is in the sequential logic circuits, not in the combinational circuit. Okay, so next, we have some examples in this. So basically, the adders and subtractors comes under the combinational logic circuit. Decoders we are having in the combinational circuit, and then we have multiplexers, code converters, ROM. All are the examples of the combinational logic circuit. Now the main thing is that how we design a combinational logic circuit. So there are various steps to design a combinational logic circuit. So these steps are basically, the first thing we have to do is like we have to state and observe the problem. So we are given with certain problem, we just have to observe that, so that we can decide on the how we can minimize it, or how we can implement the truth table for the particular problem, or what will be the number of the inputs involved in this particular problem and the number of the output. So all these things we have to decide. So the first thing in deciding all these things in order to make a combinational logic circuit is that we have to first state and observe the problem. Okay, then number second step is like we have to determine the number of input variables and required output variables. That means in the second step, first when we have decided upon the problem, what the problem is, then we have to decide upon like how many number of variables, or I can say the number of input variables will be involved in designing the particular circuit. And then we have to simultaneously decide about the output, how many output variables will be required in this particular circuit. So when we are done with the second step, then we have to move towards the third step. Okay, then the third thing is like we have to assign letter symbols to input and output, like we give as A, B, X, Y, Z. So we have to just give the name to these input number variables and to the output variables in the third step. When we are done with the third step, then we have to move towards the fourth step, that is we have to construct the truth table that defines the relationship between the input and output variables. So that means basically in the second step we will just determine the input variables and the output variables. In the fourth step, we are actually trying to solve the problem which we have stated in the first step. So that means we are just trying to make a relationship between the input and the output variables in the form of a truth table. So after just defining the truth table, which will be solely based upon the problem, so then in the fifth step, we just have to simplify the Boolean expression. So here we have to take care like how we can simplify the Boolean expression. So we can, when we are given with the truth table, we can just make a Boolean expression out of it. We can just use the key maps, or we can represent that output variables of the truth table in the form of an SOP or POS, and then afterwards we can just minimize them using the key map concept. So in the fifth step, we have to just simplify it. We are simplifying it just to simplify our logic circuit ultimately. So yeah, after fifth step, we have to just, when we are will be when we are done here, so finally we will have a simplified Boolean expression at the step first, at the step fifth. So after step fifth, we have to just draw the logic diagram. So these are the steps which we are going to follow while designing any combinational logic circuit. So to make it more clear, we will just take an example and try to implement it using all these points. So I have taken here an example to create a half adder. Okay, what is an half adder first? Half adder is basically an adder which will be used, or we can say the circuit, a logical circuit, which can add 2 bits. Okay, so our problem is that that means we have identified here the problem, which is a step first. So in the step first, we have identified the problem that we have to add 2 bits. That means in step first, we are just defining the problem. We have to create a circuit that can add 2 bits. Okay, so that means then in the second step, we have to identify the number of the inputs and outputs of the circuit. That means we have to, in the second step, as discussed already, so in the second step we have to decide upon the variables, what will be the number of the variables taken as an input, and then the number of the variables which will be taken as an output. So basically, as I am telling you here, the half adder is used to add only 2 bits, so that means for sure there will be only 2 inputs to this. Okay, then upon the output, we have to decide the number of the output variables. Output variables here will be 2. Because if you see that when we are adding 2 variables, that means like we will be having 4 combinations, because 2 variables means 2 raised to the power 2, which is equivalent to 4. So the combinations will be 0 0 0 1 1 0 1 and 1. When we add 0 to 0, it will be equivalent to 0. Then 0, when we add 0 to 1, that will be equivalent to 1 without carry. Then when we add 1 with 0, sum will be 0 without any carry. But when we will add 1 and 1, that will be equivalent to 1 0, which is basically the 2. But 0 will be the sum and 1 will be the carry bit in it. So that means here we have to save the carry bit as well. So that means in an output there will be 2 bits required, one for the sum and another one for the carry. That's why we are saying that we have to create a circuit that can add 2 bits. So for this we require 2 inputs, one for the first bit x, another for the second bit y, and 2 outputs, one for sum s of 2 bits and another for carry. So that means 2 input variables and 2 output variables. So in the second step, we have decided upon the number of the input and the output variables involved. Okay, so now in the third step, we have to just create the truth table. Okay, So how we are making a truth table? So just we are taking the combination of x and y. That means we are just deciding upon these bits, the input bits, and then we have to decide, we have to just take two variables for the output, sum and carry. Okay, so if you will see here, like for the two bits, we will be having the four combinations, 2 raised to the power 2. That's what I have mentioned here: 0 0 0 1 1 0 1 and 1. Okay, then afterwards, when I am just adding these two bits, because I am making the half adder means which will be able to just add two bits. So when I am adding bit 0 to bit 0, it will be equivalent to 0. Okay, without any carry, it is not giving any carry. Okay, then 0 plus 1 will be equal to 1 without any carry. Okay, then 1 plus 0, that will be equivalent to obviously 1 without any carry. Then 1 plus 1, that will be equivalent to 1 0, but 0 will be considered as the sum, and the 1, the first bit, which is the carry bit, will be stated here. So 1 is here, so here we are having the carry bit. So now we have decided upon the truth table. This is the truth table. The number of variables are input variables are 2, and the output variables as well are 2. Then we have just implemented the truth table. Then our step fourth is just we have to simplify the boolean function for each output. We are here working with the sum of product. Like sum of product, in the sum of product form, we just consider the number of the ones in the output variable, right? So considering that, we have to simplify our expression. Before this, you can also go for the k-map, and you can just draw the k-map for this truth table, and after drawing the k-map, you can make the simplified expression in the form of an SOP. So the sum, we are considering the number of the ones here. See, in sum, we are getting an output as 1 in these combinations when we are having the bits of opposite sign. That means here x is 0 and y is 1, we are getting an output as 1. And when we are having x as 1 and y as 0, we are getting an output as 1. That means when the bits are of opposite sign, we are getting the output as 1, otherwise it is 0. Okay, and for the carry, we are having an output 1 when both the inputs are 1. That means when both the inputs are high in a carry, we are getting an output as high. And for sum, we are getting an output 1 when both the inputs are of opposite sign. Now we can simply write an expression for the sum and carry. So will be equivalent to x XOR y, and carry will be equivalent to x and y. Because if you will see from the truth table, this is the function of an XOR gate. When both the inputs are of opposite variable, like one is 0 and another is 1, then only the output will be high. So, or the x is 1 and y is 0, then the output is high, that means 1. So we can just simply say that in a sum will be just expressed as x XOR y. SOP form, x as 0 is represented as x complement, and y as 1 will be represented as y. So therefore we will write it as x complement y or x y complement. So that is equal to, that is actually the functionality of x XOR y. Okay, for the carry, we are writing the output is high when both the inputs are high. So that means this is the functionality of an AND gate. So we are simply writing it as x and y. Okay, get using boolean functions obtaining from step 4. That means now we have to construct what? Circuit using boolean functions obtained from the fourth. So for constructing this circuit, what we need is, like, we require just an XOR gate and the AND gate. So for sum, we have obtained x XOR y, so we will connect x and y to the inputs of XOR gate and take its output as sum. For carry, we have obtained x and y, so We will connect x and y to the inputs of AND gate and take its output as a carry. So finally this will be the logical circuit, or we can say the logic diagram for the combinational logic of half adder. So here you can see that we are just having two inputs and two output. This gate is used for the carry bit and this XOR gate is used for the sum bit. The input to the XOR gate is X and Y and the input to the AND gate is X and Y. This gate is required for the carry bit and this gate is required for the sum bit. That means this is the logic circuit for the half adder. So this is how we design the combinational logic circuit using certain following certain procedures or steps. So thank you.